Hi guys and welcome back. In this video we will finish up with our first section on normed linear spaces, and once done we will then begin with the theory of Hilbert spaces, which is chapter 2 in the lecture notes. At the end of the last video I was discussing a few examples of bounded linear transformations on some normed linear spaces, and we essentially computed the operator norms for those transformations. Now, these examples were linear maps on a finite dimensional space. That is always going to be a bounded linear transformation. We discussed then 3 examples in sequence spaces: the multiplication operator, the right shift and the left shift. And they are all defined on the small LP spaces, so p-summable sequences, and we actually managed to compute the operator norms explicitly. Now here in the last example we will go back to the continuous world. So we will be studying continuous functions. That was the abbreviation C01, and that space equipped with the infinity norm. The infinity norm is the supremum of the complex modulus of the function f of x ranging between 0 and 1. Okay. Now, the operator that we're interested in is very, very famous and it appears in many applications, called an integral operator. And I denote it with capital K, and it is defined in this equation. So what does it do? You take function f here, and then it integrates f against another function in 2 variables, small k, which depends on x and y. You integrate out the y variable from 0 to 1, and then whatever results is going to be a function in x. Okay? This small function, by the way, here in the integrand is called the kernel of the integral operator. It is a function that is defined on the square, so 0, 1 cross 0, 1, complex valued in general, and we assume it to be continuous on that square. Okay, that's the operator. So it takes a function f, it integrates it against this kernel that depends on the auxiliary variable small x, and then it spits out another function. All right, that's the definition. Now, I already claim here that this is a linear transformation from Z01 to Z01. So that requires a few comments. So how do I know that if I take a continuous function small f and I stick it in here and integrate against the small k, that I again end up after integration with a continuous function? Well, this is a fact about parameter integrals in real analysis. So if you have these continuous kernels, you can easily show by a delta epsilon argument that the resulting object is indeed a continuous function. Okay, so I will just write, note that capital K, the operator, is well defined. It maps continuous functions to continuous functions. It is linear. That requires virtually no explanation because integration is linear. If you take the integral of a sum of 2 functions, it's just the sum of the 2 integrals. Okay? And by the triangle inequality, we will now check that this is bounded. Okay? By the triangle inequality, for any x in 0, 1. So let's take left hand side, capital K, f of x, complex modulus. Now the complex modulus would be outside the integral, but there is a triangle inequality for integrals that allows you to bring it inside. Then you get an upper bound, and then you have this result. Okay, now what can you do now? Well, of course, standard estimate, this f here is at most the supremum of the same quantity taken over the interval 0 to 1, which is exactly the infinity norm. Okay, and the same thing you can do in the first quantity. Well, that's in two variables. So you say this is at most, well, here, notice, by the way, I tend to write supremum. This is by my own convention. But of course, these are maxima because you're working with continuous functions on compact intervals. So the suprema are actually maxima. And the same here for this first quantity. So this is at most the maximum of kxy and xy ranging freely over the square. Okay, this maybe to save some space here, allow me to move this here as such. Okay, so what you see here is this is at most the f infinity norm maximum kxy xy from 0 to 1. Okay, this is what you get, and this immediately, since this is valid for any x in the interval 0 to 1, this immediately tells you that k is a bounded linear operator on that space. Okay, now this inequality in general does not allow you to conclude that the operator norm, right? So in the previous three examples, we actually managed to compute the operator norm. Currently, what this little inequality tells you is that the operator norm is at most equal to this red shaded quantity. Okay, but it's actually in general, it's not true that the operator norm is equal to that red shaded quantity. This is here an example where you need much more work to conclude or to compute the actual operator norm. Okay. All right. I presented this example here just to get some more practice about operator norms, or estimates at least thereof. We will encounter the integral operators later on in chapter 4 of our class again. All right. For now, this will now conclude the material on the non-linear spaces. So to pivot, we did a few things. We defined non-linear spaces. We talked about bounded linear transformations on those. We had a theorem that gives 5 equivalences for linear maps being continuous. Turned out that this is actually equivalent to being linear maps being bounded. Then we had the equivalent norm theorem. It's very important stuff because it sort of captures the essence of why finite dimensional spaces are not very interesting. After that, we discussed examples. We introduced a few spaces, in particular sequence spaces, very important. Followed then, we had the kernel range definitions. We had the space of bounded linear transformations, that being a complete space if the target space Y is complete, and now at the end we discussed a few more examples. All right, now we will move ahead. We will go to chapter 2. So in teaching functional analysis, one can take several approaches. I choose the following. So we will talk now about, well, these particular normed linear spaces called Hilbert spaces. To me, these are the most important spaces that I encounter in my day-to-day work whenever I apply functional analysis. And they are, in a sense, very nice spaces because they, of course, they are almost always infinite dimensional, otherwise it's boring to look at those. But even then, they have very much properties that you know from the finite dimensional world. That's why it's nice to work in Hilbert spaces. Okay, but let's go step by step. So up front, I need a quick definition, which is known, I hope very much known from linear algebra. These are inner products. Okay, so starting with a vector space V, let me just recall what is an inner product. So here, for simplicity, now in this chapter, I'm mostly concerned with vector spaces over the field of complex numbers, although there is no downside of doing this theory over real vector spaces, right? So but I just want, I don't want to write all the time either over f equals r or f equals c. That's why complex, okay, from the get-go. What is an inner product? Well, we will use this notation, these bra and cat brackets that maybe you know from quantum mechanics. So this is simply a map that takes two vectors and it spits out a scalar here complex number. It's called an inner product if three properties are satisfied. Those are the ones written here. Although, here in property number 1, although for general inputs x and y, the inner product can be complex valued, it is not when you evaluate it on the same vector, because the first condition here requires this to be a non-negative number, so in particular real valued. Moreover, that number is 0 if and only if, again, you stick in the 0 vector. This is the very much like in the norm world, the positive definiteness. Okay. The second property is the conjugate symmetry. So you can swap the roles of x and y and you almost get the same result. The only difference is there's a complex conjugate bar here on top. The third property is the linearity in first vector. Remember, because the inner product takes two vectors and spits out one scalar, it is only linear in the first vector. Right, so if here's alpha x plus beta y, then the alpha goes out, the beta goes out as well, and you add up the two inner products. Linearity in the first vector. If you have a vector space with a distinguished inner product on it, you call it an inner product space, exactly as it is in linear algebra. You have to be a bit careful if you read books on functional analysis. There are competing conventions as to where the inner product is linear. Some authors do it in the first vector, like I do it here in this class. Other authors do it in the second vector. As long as you are consistent, all the theory is the same. Okay, it doesn't matter at the end of the day, but you have to apply it consistently throughout. Okay, good. Few examples. These are standard examples known from linear algebra, so I can go rather quickly. If you look at coordinate spaces, c to the n, so just, n-dimensional row vectors, say, with complex entries, this is the standard inner product. This is the dot product. Okay, this is the dot product. The inner product, yeah, maybe I should say this, of course. The inner product carries a lot of geometrical meaning, at least in finite dimensions. It is a natural generalization of the dot product between two vectors, say in R2. Okay. This is the first example. This is an inner product. Of course, you should convince yourself that this is really an inner product by checking that these three properties are satisfied, but this is easy. You're dealing here with finite sums. They're obviously linear in the xj entry. If you swap the order between x and y, then you just, well, put the bar on the other vector, which corresponds to putting a bar on the total thing, and the positive definiteness is also easy to see. Okay. The next one, this is also probably known from linear algebra, continuous functions. So this is the continuous generalization of the finite sum in the dot product. You look at the integral. Okay. This is also an inner product on continuous functions. It's well defined because product of two continuous functions is continuous, hence integrable over compact sets. And now you have to check again that this here satisfies the three properties above, which is also more or less easy. The only part where you need a little bit of real analysis knowledge is the definiteness, namely when this is equal to 0, so set f equal to g, then you're looking at integral of this type. And now if this is 0, you have to conclude that f is identically the 0 function. From a geometric viewpoint, this is clear because this represents an area up here. You're integrating a non-negative function, so that area is only going to be 0, well, if the function is 0. If you want a rigorous proof, you need a little bit of real analysis. Good. Now, more interesting for us is, in a sense, the extension of the dot product on the sequence space, which is small l2. So this one here. So instead of truncating your sum up here at small n, as you do it in the dot product, because you're on the coordinate space, here you run all the way up to infinity. Good. So first off, notice this is well defined. In the sense that it really spits out a scalar as long as x and y are in L2. Why is this? Because of the Hölder inequality, right? So this here, this is just the L1 norm of the product of the two sequences I write 1 like this by definition. So x is xn in L2n and y is yn in L2n. Then this is the one norm of the product, and the Hölder inequality that we discussed in the other video tells you this here, and since x and y are in L2, this is finite. So this means here this is really well defined on small L2. Now you have to check that this is indeed an inner product. Again, 2 of the 3 properties are actually, all of the properties are easy. The linearity in the first vector is clear, because this is how you add, how you manipulate infinite series. The conjugate symmetry is also clear. You just put the bar on the first entry, which corresponds to putting the bar over the whole thing. And the definiteness, yeah, it's also easy, because you're adding non-negative numbers. Because if x is equal to y, you have an xn modulus squared. If that is equal to 0, this is only going to happen if all the xn's are equal to 0. Okay. So this is also good. This is an important inner product on that space. Much more important than this one up there and the dot product on Cn. So let's keep this in mind. Okay. Good. Now, moving ahead, a few other definitions that are also very familiar from linear algebra. So we need to make sense of orthogonal vectors, right? So the reason why one is interested in inner products is on one hand geometrical, because it encodes the notion of an angle between 2 vectors. At least that geometrical intuition works, say, in R2. Because we already have the notion of length. This is what the norm does. But now here, the inner product, it captures an angle. All right? And that manifests itself in this definition. So we say that 2 vectors in an inner product space, 2 vectors, call them x and y. And they are orthogonal if and only if, well, the dot product, I shouldn't say dot product, because in general it's not a dot product, if their inner product vanishes. All right. This is really motivated by looking at the dot product on R2, and there you can easily figure out that the angle between the 2 vectors in the plane is 90 degrees if and only if that dot product is equal to 0. And that's a generalization to, well, arbitrary vector spaces. You know, x and y could be functions, so you can't really make sense of an angle between 2 functions, but nevertheless, this concept generalizes. Good. These are orthogonal vectors. Now here we will talk about also orthonormal vectors. These are the orthogonal vectors that have length 1. So here's the definition. So a collection. So now careful here. So we are no longer in finite dimensions. So I use this notation. So here this is a collection of vectors, and each member of that collection is indexed by an index small alpha, and alpha is drawn from an index set capital I. Now in linear algebra, that I is always finite. It's a finite set. Now here in functional analysis, this set can be countable. That means it can be finite or countably infinite, but it can also be uncountable. Okay, we will have all these possibilities. Okay. But nevertheless, we can make sense of vectors being orthonormal. They have to be orthogonal. This is written here if alpha is different from beta. And then, well, the norm is already in the background, of course. We say orthonormal if orthogonal plus this condition is satisfied. Now, this, you know this, of course, it relates to the actual norm, but right now it's maybe not so clear. So what we will do is we will use this shorthand. Remember, one of the axioms of the inner product is that if you evaluate it on the same vector, it gives you a non-negative real number. So this here is always non-negative by the axioms of an inner product. So that means you can take a positive square root and it will spit out a non-negative number. Now this non-negative number is very important quantity, and it gets its own symbol, and well, it's again the norm symbol that we use for it. As it turns out, this defines a norm. Okay, so in other words, any inner product space is a normed linear space, although at the moment we don't know this yet, because we have to check it now from first principles that this is really a norm. Okay, good. Now a few other comments. Very important concept that we will explore in the exercises that probably are known from linear algebra as well is the polarization identity. So I will just show you the identity. This is, for instance, if you work over the complex number field, it is this one. So you have an identity that relates the, well, that norm that was on the previous slide in an inner product space to the inner product itself. All right, so you take all these four norms, square them, x plus y, x minus y, x plus iy, x minus iy, I the imaginary unit, and then some, you know, decoration here out front. And if you take this combination, it turns out it spits out exactly the inner product between x and y. All right, it's a very powerful identity because it allows you to reconstruct the inner product from this, well, norm, right? So this you will prove in the exercise. It's a very simple exercise. You just, well, use the definition up there, then this square root goes out, and then you stick in at one point x plus y. So you will have x plus y, and then you use the properties of the inner product. You break this down into 4 terms, and that you do for each one here. And then at the end you realize most of the stuff cancels out, and the only thing that survives is the inner product x with y. Okay, good. There's a useful observation that we will use and we will prove in the exercises. Now, for now, let's assemble a few more identities, also I think known from linear algebra. So given a general inner product space, and with this object, again, we don't know yet if this is a norm, so let's just take this as a definition here. Then we have 3 identities. Number 1 is the parallelogram identity. So x plus y, x minus y, norm squared, added together gives you squares of the individual norms with factors of 2. This has a geometrical interpretation. That's why it's called parallelogram identity. So because, well, they span a parallelogram, right? So the diagonal here, this is your x plus y, and this is the x minus y. And this says something about the length of the sides in the parallelogram. Good. More interesting is the Pythagorean theorem. So if you have an arbitrary vector y and a finite orthonormal system or set xj, then you have this curious identity here. So j from 1 to n over these, well, inner products yxj in modulus squared, and then you add this norm squared. Turns out all the j dependency goes out and you just survive with the norm of y squared. It's quite curious, but it has one very important corollary, and this is the Bessel's inequality. This is extremely powerful. It looks deceivingly simple, but it has lots of applications, and you will really learn to appreciate it very soon. How to get Bessel's inequality? Well, look here. This part and this part, this is precisely this and this. And, well, here is a length squared, so this is non-negative. So from this inequality, you just obtain an equality by dropping this term here, the second term, and then immediately you land on Bessel's inequality. So the only thing that we have to prove is the parallelogram identity and Pythagorean theorem. Maybe in the remaining minutes I will do the parallelogram, and then at the beginning of the next video I will do the Pythagorean theorem. Good. So let's get started. So the parallelogram identity, this is a one-liner. So we will need x plus minus y, these quantities. So remember, by our definition of, well, this norm, this is x plus minus y, x plus minus y. And now you just play around with the properties of the inner product. So sort of you use distributive law. First, you get x x plus minus y. Let's do, I mean, okay, this is easy, but let's do one time all the details. Plus minus y, x plus minus y. Okay, then you use it again, say here and there, x comma x x plus minus y plus minus y comma x, and then plus minus y, looks silly, plus minus y like this. All right, then you remember that you have a linearity in the first vector and you have a conjugate symmetry. So that allows you to pull out scalar factors. So this one comes out, but it gets a complex conjugate bar because it's in the second one. This one comes out without a complex conjugate bar because the inner product is linear in the first vector. And here this one comes out as is, and this one comes out with a complex conjugate bar. Yeah, but since these are either plus or minus 1, the complex conjugate bar doesn't really do anything here. So the thing that you go out with is this, plus minus yx, and then plus minus 1 times plus minus 1 is plus 1. Okay, so at the end you have x squared plus y squared, and now what you have here is plus minus, and then remember this one here by conjugate symmetry is xy complex conjugate bar. So what you're doing here is you're adding a complex number, this one, to its complex conjugate, and that is twice the real part of the complex number. Of course, if you're over the real number field, then the real part just can be dropped. Okay, so you have this. Now, of course, you see if you add x plus y squared plus x minus y squared, then these terms here, they cancel out, and these up front, they add up, so you get twice x squared plus y squared. And that's it. That's the parallelogram identity. Okay, good. In the beginning of the next video, I will do the Pythagorean theorem, and then we will move on and build up more theory for the inner product spaces. Okay, see you then.